Hello and welcome to video 53. In this video we're going to talk about multi-loop circuits. So here you can see that there are multiple branches, but because of the battery, the additional battery, you can't just do it in terms of purely series and parallel. You actually have to use something called Kirchoffs rules. There are two rules when it comes to analyzing the circuits. One has to deal with conservation of charge, called the Junction Rule. And the Junction Rule tells us that the current going into a particular node has to be equal to the current going out of that node. You can think of this almost like a river flowing or cars on a highway. The amount that flows in has to be equal to the amount that flows out. Now, how it's split up in the circuit is going to depend on the actual resistances and other parts of the circuit, but you do know that when it does split, it's got to split so that it adds up to the amount that went in the first place. So that's conservation of charge. You can't make charge disappear or appear. The second rule is the loop rule. And what the loop rule basically says is that energy is conserved as you go around a loop, meaning all of the energy that a battery puts in has to be used at some point before the current returns back to the battery. So let's take this first battery, assume that the current starts here and loops around clockwise. So if we were to label the currents, let's say that's I1, we're going to guess this is I2. You could guess the other direction, and if it comes here, this is going to be I3, and then it's going to come back together again, and that'll be I1 again. So let's say that we loop around the circuit from the battery and we go clockwise like this. This would be loop 1. For the second loop, you actually have multiple choices. There's more than more than one way you could analyze this. For example, you could loop from this battery around clockwise like so, or if you wanted to, you could even loop around. Let me get a purple, that's a fun color. You could loop around like this. What's important is that when you make your loops, you make sure to include all the elements, meaning all the batteries, all the resistors. So in this case, there are going to be three currents we don't know. We don't know I1, we don't know I2, we don't know I3, so we would expect to, in the end, wind up with three equations, and we're going to do that. So let's actually look at this particular example, and let's write in the values for the various resistors and such. And voltage 1 is given at 15 volts. Resistor 1 is given at 20 ohms. Resistor 2 is given at 40 ohms. Battery 3, and even though there's no second battery because this is the third loop, we labeled it V3, is 25 volts. And R3 is going to be 60 ohms. Before we can proceed further, we need to pick directions for the current. So it looks, since this is the positive terminal of the battery, you can tell it's the longer side. Seems reasonable, though we don't know for sure, that the current would flow out of the positive terminal this way. So I will label this I1. Then it's going to get to a node here, or junction. Now, the current may be coming this way in branch 2, going into this node, or it may be going out. It actually doesn't matter which you pick, just when you pick it, you have to be consistent with the signs you use during the problem. So this is I2. Let's just go ahead and assume it goes to the right there. And if I1 and I2 are coming in, you have to have current 3 coming out. Otherwise there'd be a massive pileup of current, and that would build up, and that certainly doesn't happen. So this is I3, and if you want to view it as a node over here, you would say similarly I3 is going to split back into I1 and I2. So let's also pick two loops that we're going to go around. So I'll use one in red. Let's pick this loop here, go around clockwise coming out of the battery, this loop isn't something that's actually in the current or in the circuit, it's just the way we're analyzing it. So we're going around the circuit in a loop, being sure to include every element in that loop. Another loop that you could choose to make might be from this battery, V3, and I'll go around clockwise again. Now that's not the only choice. You could have, as we showed in the last slide, gone around back through the first battery and around, and that would have also covered everything, but this does the trick. So we have now covered all of the elements, have at least one loop going through them. We have directions for all of the currents. Now it's time to use the two Kirchoffs rules that we just learned. The first one is the current rule, or the junction rule, and that says that the current coming into this node, which we said was I1 plus I2, has to be equal to the current coming out of that node, which is I3. Second, and I'll leave a little space here, what we want to do is go through the first junction rule, and if you come out of battery 1, you're going to have a voltage of, or potential of 15 volts. Now I'm going to do something I don't normally like to do here. I'm going to leave off the units, because when you're dealing with this, what becomes a little bit of a massive algebra, it's easier to deal with just the numbers. But because I've shown what the units are up here, that's actually okay. So 15 volts when you leave this battery over here. Then you go through resistor 1. Now the thing about resistors is resistors always take energy out of the circuit. So when current enters a resistor, it always has more energy than when it leaves. What that means is the voltage when you go into a battery is always going to be higher than the voltage when you get out. So the current going in goes through this battery, or through this resistor, and loses some of that electric potential, that energy per charge. If you remember from Ohm's law, V equals I R. That's certainly true here. The voltage that you're going to lose as you go through this resistor is going to be equal to I1 times R1, which is 20. And I actually like to write the numbers in front of I1, I2, and I3 because those are going to be our variables. So this is going to be 20 times I1, and it's going to be minus. Again, the reason it's minus is as you loop clockwise around the loop, you go to the right through resistor 1. The current goes through the right. Since those are the same direction, that is going to be a loss of energy, minus 20 I1. Then as you continue around the loop, you go through resistor 2. Notice here's different. You have current I2, and R2 is 40, so it is going to be 40 I2, but the difference is now as I loop around clockwise around this loop, I'm traveling to the left through the resistor as I loop through it, but the current is going through the right as we've drawn it. So that is going to be a positive change in energy, because as the current goes through the resistor, it loses energy. So when it comes out, you have to be at lower energy than when you go in. So if you're looping to the left through it, you're actually going to a region of higher electric potential. So it's plus. And then you're back at the battery, and this of course adds up to 0 volts. That's the rule. Let's look at the second loop. And in the second loop, when we start over here in battery 3, you have 25 volts of electric potential, 25 joules for every coulomb that goes through. And the first element that we encounter is resistor 2. Now, unlike in loop 1 in the red loop, we're going and looping in the same direction as the current. So this is going to be minus 40 times I2. And then as we continue to loop around, we're going in the same direction as current 3 as we go through resistor 3. So that is going to be minus 60 I3. And that's also going to equal 0. Now at this point the physics is sort of done. It's algebra after this. And I'm going to show you how to do it two ways. I'm going to show you how to do it using the substitution method, or as I like to jokingly tell my students, the making things disappear not in the mafia way. Because you have three unknowns, you're going to have to play some algebra games and eliminate variables until you get one variable. Or there's a really neat trick that you can use using your calculator with a matrix to do this in essentially one step, which is really pretty nifty. I know when I saw it, it blew my mind like a fuse. That's the same joke from class. But it is that interesting. In order to facilitate that, I'm going to rewrite these just a little bit differently. That will make that easier. By the way, this is supposed to be for I1 here, I1 plus I2 equals I3. And we want to put it in a form where you have variables almost like x, y, and z, but they're going to be I1, I2, I3. This would be like 1 I1 plus 1 I2 minus 1 I3 equals 0. Now at this point you may not know why I'm doing this, but I'm hoping that you follow. Similarly, for the red one, for loop 1, I can rearrange these as minus 20 I1 plus 40 I2 plus, well, there is no I3 term, but I'm going to explicitly write 0 I3 equals, and now I'm going to bring this 15 over here. That's going to have to be minus 15 when I bring it over. And I'm going to give these a name while I'm thinking of it. We're going to call this equation 2, and the only reason I'm writing this is when we play our algebra games, we have something to refer to. I'm going to call this number 1, and then let's rearrange this third one in a similar way. Here there's no I1, but I'm going to explicitly write 0 I1 minus 40 I2 minus 60 I3, and I'm going to bring over this 25, which makes it negative 25. Since these are all negative, to make life a little easier, I prefer to see it as 0 I1 plus 40 I2 plus 60 I3 equals plus 25. So I essentially just divided both sides by negative 1, and that's okay. I'm going to draw a box around this, and from here on in I shall call this equation 3. Just gives us something to refer to. We're going to come back to this in a little bit, but let me show you the substitution way of going about business. The first thing I'm going to do is I am going to rewrite this, so I'm going to substitute into equation 2, and what I'm going to substitute is I1 equals, if you bring that over, you get I3 minus I1, and I'm going to substitute that into equation number 2. And you may say, well, why would you do that? I'm doing that to eliminate a variable, eliminate I1. It makes it easier, or frankly possible, to figure out what these things are. So if you can follow along here, in 2, see how it's minus 20 times I1? If I rewrite this, that is going to be minus 20 times I3, and minus 20 times minus I1 is going to be plus 20 I1. So we've now replaced I1, and I can write the rest of this. Plus 40 I2 is going to equal negative 15. Then I'm going to simplify this, combine these, whoops, that should be plus 20 I2. I'm going to combine these I2 terms, and you get 60 I2 minus 20 I3, and that's still going to equal negative 15. And I'm going to put a box around this in case I need to refer back to it later. And I'm going to call this equation 4. Just makes it a little bit easier to refer to. And let's look at equation 4 and equation 3. So if you're looking at these are pretty similar. Let's see if I can use a highlighter. I'm going to zoom in or focus on this term here, the I3 and the I3. I want to eliminate this between the two equations. Now I can't just add or subtract these. That often works. I have to modify that approach very slightly. If this was minus 60, we'd be all set. We can just add these together and these would cancel out. Well, we can make that happen by multiplying minus 20 times 3. You just have to multiply both sides by 3 in order for it to be mathematically permissible. So what we're going to do is we're going to add, but what we're going to add is we are going to take 3, let me move this up, and we're going to add to that 3 times equation 4 that we just found. So rewriting this, I'm going to take 40 I2 plus 60 I3 equals 25. And then what I'm going to do is I'm going to take plus 3 times this 4 that we just found, this equation 4. 3 times 60 is 180, so that's 180 I2. 3 times minus 20 is minus 60, which is the reason we're doing this, so that we can eliminate this I3 term. But if we multiply the left side by 3, you have to multiply the right side by 3. So negative 15 times 3 is negative 45. And then I'm going to add those together. Notice these cancel out. And we're going to end up with 220 I2 equals negative 25. Divide both sides by 220, and you should get a current 2 that is equal to negative 0.0909 amps. So we've got one of the 3 variables that we need. We've got current 2. We still need currents 3 and currents 1, but now it's relatively straightforward, at least comparatively. So we're going to take this and plug it into here. When we do that, it's going to be 60 times negative 0.0909. Again, I'm leaving off the units. Minus 20 I3 equals negative 15. Be very, very careful when you do this math. So 60 times negative 0.0909 is going to give you a negative number. And then you're going to add that to both sides, divide by 20. And when you do that, you should get a current 3 that is 0.4773 amps. 2 out of 3, that's not bad. It's not as good as having all 3 though. So let's look at the third equation, and to do that we'll just simply use this. If I want to get I1, I will just do this over here. I'll pick a different color because I can, and that's going to equal I3, 0.4773 amps, minus negative 0.0909 amps. And when I add those, that is going to give me plus 0.5682 amps. And we have done it using the substitution method. But oh no, we're not done. I would like to show you something else, something that blew my mind when I first saw it. I'm hoping it blows yours, or at least you find it interesting. And that is how to use that fancy-dancy calculator that often sits in your backpack that you rarely use, at least rarely use to do more than simple math. Remember when I made you write these equations like this in this form, I1, I2, I3? I had a reason to do that, and I will let you in on the trick now. So I'm going to take these coefficients, 1, 1, minus 1, 0, minus 20, 40, 0, negative 15, 0, 40, 60, 25, and put them in what's known as an augmented matrix. Huh? Basically, you take the three variables, write their coefficients from each equation, 1, 1, minus 1, negative 20, 40, 0. That's why I explicitly wrote the zeros. 0, 40, 60. And the reason it's an augmented matrix is we include this part as well. So that's 0, minus 15, 25. And what we're going to do is we're going to put that in our calculators. So let me show you how to do that, try to talk you through. I realize calculators changed, and some of you with the TI-89, I haven't had really a chance to play with it, so best of luck as far as accessing these functions. But what we're going to do is we're going to enter this matrix into your calculator, and then we're going to put it into, or use the calculator, one of the math functions, to put into what's known as reduced row echelon form, rref. These will be one of your math functions in the matrix menu. And when you do this, you're going to wind up with something that looks like this: 1, 0, 0, and a number, 0, 1, 0, and a number, 0, 0, 1, and a number. This will be I1, this will be I2, this will be I3. So in the world's cheapest Elmo, I have a $7 webcam connected to my computer that's also focused on my calculator. Mine happens to be a TI-83. I've done this on the 84. It works exactly the same way. We'll see how we can do. So first thing we want to do is turn it on. No surprise there. And you're going to go to second and 1, 2, 3, fourth button down, matrix. First thing you have to do is you have to go to edit so that we can enter this matrix. You have to tell it what size the matrix is. As you can see, this is 3 rows by 4 columns. So you're going to hit 3, enter, 4, enter, and now you're going to type the numbers in. So if I hit 1, enter, it's kind of nice, it brings it right in. 1, enter, negative 1, enter, and the last one is 0, enter, negative 20, enter, 40, enter, 0, enter, negative 15, enter, brings us to the third row, 0, enter, 40, enter, 60, enter, 25, enter. Now this is the part that actually throws people off the most in terms of using this in your calculator. You have to quit out of the matrix before you can do other stuff. So what you do is you just hit second, quit, brings you to your regular screen. You're going to hit second, matrix. So that's second, matrix, and you're going to go over to math, and then you're going to scroll down until you get to the option that is rref. For this calculator, that is B, right there. So I'm going to hit enter. Now to put the matrix in, you have to do it again in the sense of second matrix, so second matrix, and you're just going to scroll down to the matrix you want. In this case, it's matrix A. And you hit enter, and this is when the magic happens. As you can see, we should get the same numbers we got before. I know you can barely read it on the screen, but we got 0.568, negative 0.0909, and positive 0.477. If I blow this back up, hopefully those are the same numbers we got. And they are. Negative 0.0909, positive 0.4773, positive 0.5682. Now this negative sign on the current, if you look back at the drawing we made for I2, see how we chose it going to the right? Well, turns out it's going to the left. That's okay. Can't guess them all right. Don't go back and change your picture because you want this current to match the signs you chose when you filled it in. The last thing I just want to mention, it took me a few minutes to figure it out, but let's say you want to get rid of this matrix in your calculator because you're having too much fun doing circuit problems and you filled up all your matrices. It's a common problem. If you want to fix that, what you have to do is go to second and then hit mem, which is above the enter key. Scroll down to memory management, that's option 2 on this calculator, and you're going to scroll down to matrix, hit enter, and then you just hit the delete key. So as far as what you have to be able to do on a test, at least for me, for my students, my expectation is that you can correctly apply Kirchoff's rules, both the junction rule, conservation of current, and the loop rule to the appropriate number of loops, in this case 2, so that you've captured all the elements. At that point on a test, I'm not going to require students to use the substitution method all the way to the end to get the 3 currents. There's a lot of time involved and opportunities for mistakes. If you can show me the matrix in this augmented form exactly as you would have plugged it into your calculator, and you show me the currents that the calculator spits out, personally, for me, that's fine. If you're not one of my students, I'm not sure what to tell you, but I think a lot of physics teachers feel the same way, in that once you've applied Kirchoff's rules, the physics sort of stops. I hope this helps. It's a little long-winded, but this is one of these things that students often struggle with when they deal with circuits. If there's any step you don't fully understand, I recommend going back and looking at it very carefully. I can't emphasize enough, it's not a reflection on you if you pick the wrong direction. Too many students look at a problem and they say, I don't know what direction the current goes, so they don't pick any direction and then they're stuck. Go ahead, pick a direction, be confident, and do good work.